Now, there are some situations which, on their surface, seem like they would be well modeled with exponential growth or decay functions. Population, for example, is a really good intuitive way of looking at exponential functions, and so we use that example a lot. Say you have a population of rodents that we know doubles every 3 weeks or something like that. But eventually you would see that curve, the rodent curve, going to infinity. But we live on a finite planet. The number of rodents can't go to infinity because eventually there would be no food for them and they would stop reproducing. That is where the logistic growth curve, or the logistic decay curve, comes in. So this is a slight variation on exponential growth. We call this logistic growth. And it measures a population over time. It's a little more complicated looking. We won't get into the derivation of the logistic growth curve function, but we will describe some of its pieces. We call C the carrying capacity. All right, A, B, and C are always going to be real numbers, and C is always going to be positive. The reason for that is the carrying capacity represents ultimately the sort of asymptote that your function approaches. So if we had a carrying capacity of 20,000 rodents, our population would gradually kind of settle down to something around 20,000. Now, this model could be describing either growth or decay. If if b, the quantity here in the exponent, is positive, get right in there, if b there is positive, then we say that this is a growth model, and our curve will do something like this. So it grows and then kind of settles down. On the other hand, if this is a decay model, our population will start at a certain number and decay exponentially, but eventually level off at, again, that carrying capacity. So the carrying capacity represents the asymptote that this function gradually approaches. This one would have a carrying capacity somewhere down here. So let's look at an example that actually involves some numbers so we can get a feel for this. So in this exercise we have a group of archaeologists participating at a convention. They go to a remote island to study a recently discovered culture. While at this island, the group is exposed to a contagious virus, and we're told that each archaeologist infects another member of the group every 3.5 hours. Once infected, the person will become immune to the virus. The number of archaeologists infected with the virus after T hours is given by the following logistic function. So, why do we care that they become immune? Well, that means that the number of people that can be infected goes down as more people become infected. So, the first thing we want to identify is the carrying capacity. The carrying capacity, they've named it rather conveniently for us, would be C. How many people can be infected? There are 239 archaeologists, one assumes, so 239 is the carrying capacity. Now what this population model does for us is describe the population afflicted after T, in this case hours, after time. So we are given this model and we can say what happens when T equals 3. Well, P of 3 would be, and this gets a little large, 239 divided by 1 plus 125 times e to the negative 0.9235, and our input is 3 hours. Now this can be plugged into the calculator, and it would probably be a good idea to do so. Our carrying capacity, 239, will get divided by 1 plus 125 times e to the negative 0.9235 times 3. Alright, I'll close off my denominator parentheses. And before we hit enter, again, what numbers make sense as answers? We want to know how many people are infected after 3 hours, so it's going to have to be more than 0, right? At least a few people are infected at this point. On the other hand, we also know that the total highest number of people that could be infected is 239. So anywhere between 0 and 239, not including those values, would be a good answer. And we, if we hit enter, come up with approximately 27 people are infected at this time. And that kind of makes sense. After an hour and a half, the first person who is infected infects another member of the group. Now those people can all infect one member of the group in another hour and a half. In the next section, we want to know, when will 60 people be infected? So in this case, we are looking for time. So what do we have to go on? Well, we know the population goal that we're talking about. So we know that P of t is 60 in this scenario. Well, what does that mean? Well, we have a model for this, so if we set our model equal to 60 and then solve for t, we'll be good. Alright, so that means starting place would be 60 equal to 239 over that whole wacky denominator, 1 plus 125 e to the negative 0.9235 t. Okay, so where are we? We have t in the exponent of the denominator. So this one is a couple of different things at once. It's going to resemble an exponential equation, which means we want to isolate the base to the power. But that is in the denominator. So this is also, in essence, a rational equation. Whenever we want to deal with a rational equation, we want to clear the fractions. So if we multiply both sides by that whole denominator, that would be 1 plus 125 e to the negative 0.9235 t, left and right, we will end up with that. Switch back to the right color, times 60 on the left. 1 plus 125 e to the negative 0.9235 t times 60 equals 237. Okay, so we're making progress. Now it's no longer a rational equation that we have to worry about, but we still want to isolate the exponential part. E, we'll get that by itself. One nice way to do that might be to divide both sides by 60. Get rid of the parentheses that way. Okay, now I'm not going to round anything until I get a little closer to the end. So what does that leave us with? Well, on the left, our fractions cancel. On the right, we're going to have whatever 237 over 60 is. So for now, we've got 1 plus 125 e to the negative 0.9235t equals 273 over 60. Okay, so now we still want to get e by itself. There are a few ways we can do that. Foremost, I think we could probably subtract 1, right? Get rid of the 1. And then that will leave us with 125 e to the negative 0.9235 t equal to 270, should that be 273? Sorry, 237. Oh, that should be 239. What am I doing? Losing track of stuff all over the place. 239 was our carrying capacity. 239. 239 over 60 minus 1. All right, and we're even closer. So now, to isolate e and its exponent, all we have to do is divide by 125. So how would that look? Now we've got e to the negative 0.9235t equal to 239 over 60 minus 1, all divided by 125. Okay, so now might be a good time to go to the calculator, do an approximation. E to the negative 0.9235t is approximately equal to, and we'll carry this out to a few decimal places. What is 239 over 60 minus 1 over 125? I am coming up with 0.023866.7. Okay, now we're almost there, I promise. We've got e by itself. If we're solving an exponential equation, that is the first goal. Now we can get the exponent out by ln'ing both sides. In this case, we're logging both sides with the same base that we have. That's e. So if we ln the left side and ln the right side, our ln and our e will cancel, and we'll just get what's inside the exponent, which is negative 0.9235. That's a 5 times t equals the natural log of all that stuff, 0.02386667. And finally, we're just about there. We can solve for t at this point by dividing by everything that's not t. That means negative 0.9235. so our exact answer for t, we could say, or pretty close to an exact answer, is the ln of 0.0238667 over negative 0.9235. But we're talking about time. We want to know how long this is really going to take. So if we go to the calculator, we've got the ln of 0.0, or the answer that we just had. And if we divide that by negative 0.9235, we'll end up with a value. Now before we hit enter, just like in other cases, it's a good idea to think about what values would make sense. On the previous exercise, we said after 3 hours, 27 people will be infected. So my intuition is suggesting that it's going to take longer for more people to be infected. So if we hit enter, we end up with 4.04. In other words, it's going to take approximately 4, and our units here are hours, for this to happen, for there to be 60 infected archaeologists. Alright, so that is a great capstone question that covers a lot of different techniques, getting stuff out of an exponent, solving a rational equation out of the blue. I want to look at one final type of exercise, and that is involving carbon dating.